Um, we got to start, and I don't know if we are recording or not because it looks a little bit strange. Let me see. All right, I think it is starting. Um, so let's just continue our discussion about the triple integral. As in the last segment, we did go through one example about this triple integral. We set it up, the integral in a box, which means all the limits for x, y, z are in data constants. And we are able to set up the iterated integral in this nice and easy way because all these bounds are constants, right? And this is not a typical setup for us to compute. And what we should concern about is indeed those general regions like this. And I think last time we discussed this projection of E onto the xy plane, all right? And over this xy plane, the projection D could be a type 1 type 2, and the same idea could be applied to other region. If, for example, the projection of E onto the other plane is easier, for example, in here, in the 1 and the 2 diagram, the E in Y is projected to the YZ plane, and in the 2, the E is projected to the XZ plane. Okay, so the idea is still, again, let's look at this so-called type 2. We project this E region onto this YZ plane, as illustrated in the left panel above. And we can see the X variable is having the lower bound and upper bound to be determined by two variable y and z. All right. And on the other hand, if you project it as a type 3 to this xz plane, and then the y variable will be bounded by two functions that depends on the x and the z. So first of all, we kind of like treat this piece as the most interior layer and this piece as the most interior layer, right? So first of all, we project this E onto here to the YZ plane, all right? And then what you should imagine is that by standing at one point on this D, you shoot a laser over your head, all right, straight up. And then, but that straight up is parallel to the x axis. And then you have one limit, lower limit for the x, and you have an upper limit for x. And its lower and upper limit will be depending on y and z accordingly. And similarly, we can think about this second case on the top panel on the right. All right. And then this E is projected on the x-y plane. That means the y variable um, will be changing. What you should imagine that you can stand at a point on the x plane, xz plane in the D. You shoot a laser up above your head, and there will be a lower limit and an upper limit for this y variable. And those lower limit and upper limit will be determined by the x and z coordinate of the point where you stand accordingly. So this is the idea for us. And we do have to use a lot of the um, visualization, and we also have to think about those carefully when we look at a different integration problem, because for different domain and a different integration, we might have to project or domain integration the volume onto a different plane to make the calculation easier. That is the fundamental idea. Okay, so now let's look at something that is a little bit more straightforward. Suppose we do not have to figure out the projection ourselves, but instead it is already given like this. All right, so here you can see this is for the y variable, the most interior layer, and then we have the middle layer, which is for the x variable, and the exterior is for the z variable. So how do we calculate this integral? Well, over here, we're integrating about the y variable. So the antiderivative, let's look at it here. The antiderivative of x times e to the negative y dy will be x times the integral of e to the negative y dy. All right, so this is what this is. I think x times negative e to the negative y. So this is the antiderivative, which is what we have here. And we will evaluate this antiderivative at the two different values for y. The lower limit for y is 0, and the upper limit of y is log of x. So this gave us the calculation accordingly. All right, so this is, I think, negative x times e to the negative log of x minus negative x times e to the negative 0. So dx dz, this is what we have. And then what? Then we can figure this out. So it is 1, 2, 0 to z. And what this is? This is this piece. Let's write it above. E to the negative. Well, let's write it here. E to the negative log x is equal to e to the log x, and here to the power -1. And this is also called law of logarithms. So this is x to the power -1. So x times x to the -1 is indeed just the constant one, right? We have to keep that in mind. So this is a negative x times x to the -1, and a minus minus another negative. So this is plus x times 1. So this is what we have. So this is the x minus 1 indeed over here, and the antiderivative of that about x variable is, let me write it down here. So this is x minus 1. All right, so the antiderivative of that about x is x squared over 2 minus x, and x equals 0, and x equals 2z. All right, so this is equal to 2z squared over 2 minus 2z, subtract x equals 0 is just 0. Easy. So we have here, so this is becoming 4z squared over 2, which is 2z squared. This is the integral for z from 1 to 2. So this is 2z squared minus 2z dz, right? So we have what? So we have the antiderivative figured out for this is 2 times z cubed over 3 minus z squared for z between 1 and 2. So when z equals 2, we get a 2 times 2 cubed over 3 minus 2 squared minus, when z equals 1, we have 2/3 minus 1. And then you can finish the calculation. uh, afterwards. So this is relatively easy because for this type of the integral, the iterated integral is already set up. Okay, so here the question is iterated integral is already set up. We just need to evaluate the integral by finding the antiderivative from the interior layer to the exterior layer. Okay, so those are relatively easy problem. All right, and then now let's look at something that is a bit more challenging. So let me write down this example first. So set up this triple integral, and the integrand is constant 1, and the volume is the solid. The volume E is a solid bounded by two interface. The first is the Z equals 100 minus x squared minus y squared. And the second surface is a Z equals x plus y minus 2. Also, and this solid is above the rectangle. One 3 times 2 4 in the xy plane. Obviously here x is between 1 to 3 and y is between 2 and 4. Okay, so here things are quite straightforward if you try to imagine. Because here, what we should think of is that in the xy plane, 2, 3, 3, 4, so 1, 3, 1, 2, 3, 4. In the xy plane, we have our projection of E onto a xy plane will be this rectangle. Would you imagine that you can jump onto any point of this rectangle? So here, the E is represented by xy in D, all right? And then the Z variable will be determined by what? By two curves, U1 xy and U2 xy as the notation we have. And here this D is the rectangle. X is between 1 and 3, and the Y is between 2 and 4. Okay, so this is a D. Obviously, our focus here will be at determining the two lower and upper bounds for this variable Z. And this is not so difficult to figure out. The Z is between those two curves, but which one is on top and which one is the bottom? That is question we should answer. Okay, so now we can we already have some rough idea what this D is. We already know that z is bounded by u1 and u2. Obviously, we have to solve u1 and u2 or z from those two surfaces. Which one is on top? Which one is below? Well, one thing we should notice is the second one is a plane, right? If you move the z to the right, it is becoming 0 equals x plus y minus z. And you move the 2 to the left, then you got the plane equation. And this one, well, this one is a quadratic surface, all right? And how do we get the sense that which one is on top, which one is below? We can do this. We can pick a point, xy, that is in D, to actually see which z is giving us a larger value, which one is smaller. All right, so what we could do is that by picking x equals 2 and y equals 2, we'll see this z is bigger and this z is smaller. So the plane is the bottom edge of the volume, and the z equals 100 minus x squared minus y squared is indeed the top edge. So the domain could be written in this way. How about we combine this representation of a D? So this x is between 1 and 3, y is between 2 and 4, and also z will be bounded below by this line, and above, oh, this. Okay, so with this representation, it's relatively easy for us to set up the iterated integral now, which is, so the integrand is 1, and we choose, obviously, the interior variable will be z, coming from here. The lower bound is x plus y minus 2. The upper bound is 100 minus x squared minus y squared. And then, because x and y are having constant bounds, so it doesn't really matter which one we integrate first and which one we keep as the exterior integral variable. How about we just keep the order z, y, x? So y is between 2 and 4, and x is between 1 to 3. So this is how we set up the iterated integral. Okay, so we could compute it, but the question is only asking us to set it up. So this is our result, all right.